Dr. Masato Origuchi from Renault. He is the Chief Battery Engineer for EV and HEV in Renault. So please introduce yourself.
Yes, I can. Thank you very much for your introduction. Yes, my name is Masato Origuchi. I am working for Renault. I used to work for Nissan a long time ago. I was part of the development team for the first lithium-ion battery in Nissan for United States. And then I moved to Renault 2002. So I'm always in charge of the battery development in Renault. And I'm very happy to be here after developing such new electric vehicles using new lithium-ion batteries. So today I'd like to introduce our lithium-ion batteries. So the first part is introduction of our current electric vehicles, Zoe and its battery. And the second part, I would like to talk about the next generation batteries, what we expect. And the last part, I will cover some of the EV applications. That means more than EV, so like hybrid vehicles and so on. So, but I think it's somehow difficult to make a presentation just after a very nice presentation with very rich contents. So many things are already given, but I will try my best. So before talking about our EV batteries, I just like to share here our achievement since this new era of the electric vehicles. We started from Nissan side, started from 2010 with the famous Leaf, which is always leading this EV market. And they are doing very well, and they sold in last year more than 60,000 Leaf per year. And they added also a new commercial van using the same battery, ENV200. And Renault side, we started from 2011 with Kangoo electric vehicle, mainly for the commercial delivery, and using the same batteries supplied by Nissan and AESC. And second vehicles, Fluence, this was developed for dedicated for better price Israel, but unfortunately they disappeared. But we still continue this vehicle. Now it's not a Fluence anymore, but it's SM3, the same vehicle made in Korea, Renault Samsung. We updated the powertrain and the batteries supplied by Korean supplier. And the third one is the Twizy. This is a very unique commuter vehicle. It's not a car category, but it's a very funny vehicle. And recently I read that through Nissan, this was introduced in California market. So it's, I think we saw the one Twizy in the exposition, maybe you can see. And the last one, I would like to detail more about the Zoe. But anyway, from 2010, so we are always leading this electric vehicle market. And the most important point here is that this growing speed of the EV market is much, much faster than that of the hybrid vehicles when Toyota launched their Prius into 1997. So let's talk about our Zoe vehicle and its battery. So here I think you already somehow saw this picture, the skeleton view of this Zoe vehicle. This is a vehicle specifically developed for electric vehicles. This is not a conversion from the conventional vehicle, but just like a Nissan Leaf, it's a dedicated platform so that we can obtain, let's say, ideal place for the batteries, which is under the floor, the center of the vehicle, well protected from every direction of the crash of the vehicle. And this year, beginning of this year, we slightly updated our Zoe. So I just would like to explain. The first point is the powertrain, electric powertrain called R240. This is newly developed in-house development and also manufactured by Renault ourselves. providing about 65 kilowatt power, and also 22 kilowatt AC charger is integrated in this powertrain using motor and inverter to provide the charging conversion from AC to DC to charge the battery. And the battery side, we very slightly modified to increase the usable energy from 22 kilowatt hour at the beginning to the 23.3 kilowatt hour. Yes, it's just a mistake. To achieve 240 kilometers in NADC mode. This is just an NADC, it's not a real driving cycle. So by a high efficient e-Powertrain newly developed and also the batteries, we could achieve 240 kilometers. So this is a global view of the batteries. I need sometimes such a nice picture to explain to our top directors who doesn't know what is the batteries, but I believe you are involved in the battery development, so it's not maybe quite obvious. We have battery cells inside the modules, and we combine several modules inside the pack, and we add some electronics and sub disconnect switch and so on to construct a battery pack system. And this is another view of the battery pack, which is installed in the way. So as I said, it has a 23.3 kilowatt hour energy, about 280 kilograms weight. Battery pack lower case is made of extrusion aluminum material, and upper case, this is photo shows like aluminum, but it's still steel. Formed steel cover, and we have 12 modules inside this pack, and this pack battery is air cooled. We have a dedicated HVAC system just behind this battery pack, and using the air conditioning system of the vehicle to cool the battery. And we have, of course, a service disconnect switch. And one thing which is not written here is that this hole of the cooling air inlet and outlet, we also use in case of extreme accident case, like someone put the fire on the vehicle and the battery could catch fire. I think probably you know that to extinguish the fire of the vehicle and the battery is very, very difficult. So that we use this hole to pour the water. We discussed a lot with the fire department, and we made a lot of tests, and we use this hole to extinguish the battery, which works very, very well. What we call fireman access. Here is a picture of the cell and the modules inside the doorway. So this module is supplied by a Korean battery supplier, LG Chem. And we have 36 ampere hour cell capacity, and 16 cells inside one module connected as 2 parallel and 8 series. So totally we have 96 series and 2 parallel, so 192 cells. If you calculate the 36 ampere hour and the nominal voltage is roughly speaking 3.75, 192, you can obtain actually 26 kilowatt hour total energy. But we just give 23.3 kilowatt hour as a user energy for the customer. I just would like to explain in the next slide why we do that. So this is an image of the typical battery degradation around to the ear of the use. Especially because of the manganese chemistry that we are using for the first generation, we have let's say relatively big initial capacity loss. And if we give this total capacity to the customer, yes, customer can have maximum capacity first several months, but after 1 year maybe he will never obtain the initial capacity. That's the reason why we defined different state of charge range that we provide to the customer, what we call user state of charge here, and along to the state of health or degradation of the battery, we increase the this range of the usable state of charge, what we call smart SOC management. And by doing that, one point is that we can extend somehow the durability, and also we can provide a very flat, constant energy and performance to the customer. This was strongly requested from our product performance group. And this is the result of the current ZOE. We collected about 17,000 ZOE on the road. Because we are doing the leasing model, we have also the system to collect the battery data from the customer in real time. And this is the state of health data of the 17,000 ZOE. Still, it's not more than 3 years because it's quite young. But by explorating this trend, you see at least around 4 years, customers have 100% performance even with the manganese system. And if we extrapolate here, we can obtain easily 10 years life. This is a result of that way. So the next part, I'd like to talk about the expectation on next generation EV battery. So this slide is already shown by one of our directors, and also probably you hear that our president, Mr. Carlos Ghosn, said several times that we will double the driving range in near future. So here, the first generation Nissan Leaf and our ZOE, we provided only around 200 kilometers. Again, here is the NEDC cycle driving range. It's a different vehicle size, so this is different. And today, 2015, we upgraded to 240 kilometers by slight modification of the software of the battery and also the high efficient e-powertrain. And the Nissan side also, they just announced that new batteries go to 30 kilowatt hour to reach 50 kilometers driving range in NEDC, which will be on the road end of this year. And in very near future, our target is to extend to 400 kilometers. And the long term, let's say, target beyond 2020 is to go beyond 600 kilometers NEDC driving range. So now the question is how to achieve such an improvement. I think that most of the part was already explained by Bosch presentation, but I just like to summarize here. This is very basic principle of the battery system. So this is an example of the pouch type cell because we are using the pouch systems, but it's common for the prismatic or cylindrical cell. Lithium-ion battery has always positive electrode and a negative electrode and separator and electrolyte inside the envelope. So if we can look closely this electrode stack, we have of course the active material, cathode active material and anode active material, and also the non-active material like current collector foil or the separator and so on. And three main axes we need to work. First one is, of course, the active material, which very detailed was explained in the previous presentations. We are talking about, for example, the nickel-rich NMC material for the cathode, and adding the silicon-type material to the anode, graphite blending system, and so on. So this can improve significantly the capacity of the material itself. And the second point is the electrode design. Of course, we need to increase the ratio of the active material compared to the non-active material. So that's why we need to put what we call high loading. That means the thickness of the active material part to be increased. and at the same time, we need to make a very high dense electrode. That means a low porosity electrode design. Without sacrificing the ionic conductivity of the lithium ion. This is the biggest challenge. And other non-active parts, yes, we need to reduce such a volume, like a separator thickness or foil thickness. And also the cell design, we need to increase the electrode volume inside cell. So by doing all such stuff, how we can improve the energy density here. So today, the first generation batteries using manganese system, we had around 300 watt per liter energy density because of the pouch design, and 160 watt per kilograms of weight energy density. And 2020, we are asking to the battery suppliers to reach 700 watt per liter with 300 watt per kilogram energy density. So this can be achieved by we believe that the nickel-rich NMC type material with silicon blending system, we could achieve 700 watt per liter. And maybe the end of this decade, maybe we can reach 800 watt per liter or 350 watt per kilogram. But we see that this could be the maybe the limit of the lithium-ion technology. And so beyond that, we definitely need a post-lithium-ion batteries. If we are talking about 1,000 watt per liter or 500 watt per kilogram, this is definitely needs post-lithium system like all solid-state batteries, which already explained. So now I'd like to talk about when we increase such high energy density, we need to talk about the trade-off between the performances, because we are always focusing on the energy density, but we should not forget all other performances like power density, the safety, and chargeability. This is also a very, very important factor for the electric vehicle battery, and the durability, let's say cyclability. And the last part is the cost, but to make a same direction of the radar chart, we put inverse of the cost, so what we call affordability. It's the same with the cost. So if we say that this is the current level, and if we increase the energy density to, let's say, more than double, fortunately, this is the same direction to reduce the cost per kilowatt hour. So affordability will be improved. And we think that the power, as far as we put the same amount of material, we will not sacrifice so much power, because we are not using the limit in terms of power of the battery system today. And the safety, there is a discussion, but I did not want to put the safety as a trade-off. So I put here safety is a mandatory. We need to keep the same level all the time. And the two difficult points is the chargeability and the cyclability. And so the first point is we need to definitely improve the cyclability. And I just would like to explain what does it mean. Here the curve of the on the battery energy, usable energy as x-axis, and the number of cycles required over the life as a vertical axis. And if we are talking about, let's say, 40 megawatt hour accumulated distributed energy necessary all over the life, which corresponds to, let's say, around 200,000 kilometers or 180,000 kilometers, or such realistic vehicle life. And so the current generation battery, we have around 20 kilowatt hour, let's say, usable energy, and we have actually more than 2,000 cyclability. So we can reach around 40 megawatt hour line with current batteries. And if we increase the capacity to 40 kilowatt hour, let's say. So the driving range can be doubled. So as already discussed in the Q&A sessions, if we increase the capacity, we could reduce the number of cycles proportionally. So the 2,000 cycles can be only 1,000 cycles. And the extreme case is, we don't know exactly what they are doing, but like a Tesla vehicle, Tesla model, if we have a more than 80 kilowatt hour battery pack, maybe 500 cycles can be accepted. So, but this is if we can take same megawatt hour requirements. But in reality, if we have only 20 kilowatt hour, maybe the annual driving mileage is smaller. But if we increase, maybe the annual customer driving range will increase. Actually, we see from the data from the DOE, we see the average driving kilometer is around 10,000 kilometers per year. This is the first generation vehicles. But if we increase the driving range to the double, maybe it could increase to maybe 50,000 kilometers or 20,000 kilometers. So the 40 megawatt hour line needs to be improved. So we just talk about the durability. And then the next point is the chargeability. I don't have any beautiful slides to explain this point, but I believe this is quite obvious that even if we increase the driving range to, let's say, 300 kilometers or 400 kilometers or even 500 kilometers, some cases customer needs to charge in the middle of his trip. This is the truth. And also, in fact, the time of charging is one of the blocking points of the electric vehicle, so we definitely need to improve the charging speed rate. Today, our battery is capable to be charged at, let's say, 2C rate. Like Nissan Leaf is applying CHAdeMO charger up to 550 kilowatt charging. And at Zoe case, we are applying 43 kilowatt AC charging. And it's corresponding to around 2C rate. And if we go to 40 kilowatt battery pack, unfortunately, we cannot keep 2C rate charging, but we need to reduce to 1C rate charging, something like that. So, but in terms of power, yes, we can keep around 40 kilowatt charging power, quick charge, but it's no longer quick charge because it's still 1C or even less than 1C. So we definitely need to improve the charging capability with such a future chemistry. This is one of the hard points today. So then the last part, I would like to talk about the other than EV applications, what we need as a battery. This is the panoramic view of all our applications, electrifications from, let's say, stop-start. This is not exactly the electrification of the vehicle, but the 12-volt system. And we have a 48-volt mild-hybrid system, full HEV. Renault side, we are not working on this point, but Nissan is working full HEV system. And plug-in hybrid vehicles. This is also German OEMs are developing a lot the plug-in type vehicles and electric vehicles. And this is the usable energy, log scale usable energy, and charge discharge power as a vertical axis. And if we look at a different view of the ratio between the energy and power, it's already said the power energy ratio from the previous presentation. The EV batteries, we are talking about, roughly speaking, around 3 power and energy ratio. And a plug-in type hybrid, it depends on the vehicle requirement, but we are talking about around 8 power and energy ratio. This is, let's say, high energy type batteries. But hybrid battery is totally different, and now we are talking about around 50 power energy ratio. And especially if we are talking about a 48 mild hybrid system, this is an extreme case. conventional hybrid batteries, we see around PE ratio of around 30. But the smaller the system is, the battery is, the more severe the requirements. This is the fact. And especially the 50 C-rate charging is very, very difficult to apply to the conventional graphite or even hard carbon system. So we definitely need a new technology to achieve such extreme performance. And this is the same graph of the previous one, the capacity and the required cycle life, but the axis is inverse. So we just talk about the relationship between the energy, usable energy, and the required cycle life for the electric vehicle case. The current EV, we have around 20 kilowatt hour, 2,000 cycles, and if we improve to the 40 kilowatt hour, we can probably reduce to 1,000 cycles. That already said. And if we add here plug-in type hybrid vehicle, because the battery is very small, and maybe the number of charge will be increased because maybe the customer will drive the electric to the company in the morning, and they will charge at the company, and they will come back as the electric, so that twice a day, not just once a day. So we will definitely double the number of cycles required. And so we estimate roughly 4,000 cycles will be required for the plug-in type hybrid vehicle battery. And an extreme case is the 48 volt mile hybrid batteries. This is also how we manage the hybrid system, but we estimate a severe case to 20 watt-hour per kilometers charge amount, charge or discharge throughput. And also it depends on what size of the battery we put. And we are trying to minimize the size of the battery, let's say around 200 watt-hour. So in that case, we need more than 20,000 cycles, equivalent cycles of the durability. This is really, really severe for the conventional carbon, NMC carbon system, for example. That's why we are trying to apply a totally new battery system. And this is the last page of my presentation. But, in last month, Frankfurt Motor Show, we just announced new Megane. And in this Megane, we have one version called Hybrid Assist to achieve the fuel consumption of 3 liters for 100 kilometers, and CO2 emission reduced around 10 grams, so to reach 76 grams per kilometer. So again, this is NDC. And we are putting the really new innovative battery inside 48 volt system. And I will be very happy if I may have a chance to present to this technologies next time. This is the end of my presentation. Thank you very much.
Thank you, Dr. Origuchi. Any questions?
Hello. So my question is regarding the temperature inside the battery box. So you said you need this cooling system to keep this cool, okay? So what's the range of temperature that you need for the good performance of the battery?
The battery is, as I explained, air cooled, and ideal temperature is something around 20 to, let's say, 40 degrees C. But we can go up to 55 degrees C, or we should not exceed 60 degrees C. This is maybe the common for lithium-ion batteries. And also the lower temperature side, we don't want to be below 0 degrees C.
Matthias Bock from SGS. Are you planning to give your customers an upgrade path for improved batteries? Because your customers are buying cars and now the battery life gets better. Do you provide that as a service to your customers, and what are the costs for such things, for expansions?
This is not yet announced, so it's not easy to explain, but yes, we are trying to because we are doing the leasing model, we are not selling the batteries. Yeah, so this is one of the advantage. So the customer, if they want, they can upgrade the battery.
But who's paying for the change? Because you have to disassemble the battery.
Yes. So this is not yet announced. So
okay.
I think our business team will study now.
Okay. Any more questions? Okay, so thank you very much.
Thank you very much.